Enolate discussion today. As per usual, I will be commenting in the comments below after the video converts and giving you the start time for the lecture. All right. Got the Survivor shirt today. Oh, there's the boy. Whoa, watch what you're doing, dude. There's a heater right there. You're going to bang your head. You do a dance off again today? Can you guys see me all right? I guess you guys see me? What are you doing?
I'm the teacher today. The teacher.
You're the teacher today?
Yes.
All right.
Just kidding. Yep, another dance off.
What kind of dance off are you going to do today? What kind of dance off?
I'm thinking of first, we're all doing the floss. We're always doing the floss.
Do the floss?
Mm-hmm.
Go. He's going so fast you can't even see his arm from the video.
Not your turn to do the floss.
My turn to do the floss?
Yes. Another dance too. I have 2 more dances.
You got 2 more dances? All right, he's going to give 2 more dances, then we'll start. What is that?
I don't know if it's a Fortnite dance, okay? He doesn't know these.
Don't yell, don't yell.
He doesn't know these. And I'm the only one that knows them.
I don't watch YouTube like he does.
Yes. He doesn't know, so he keeps making fun.
All right, go watch your tablet. I'm going to lecture. All right. Am I offline again? Yeah, I had some lag. Hang on, let me turn off the Wi-Fi on my phone. That usually helps a little. How is it now? Is it better now? You missed the floss, man. All right, so hopefully you guys are okay now. Let me get my phone out of the way. Yeah, guys, so let's go ahead and get started here. So today we're going to go ahead and finish up the Enolate discussion. I was actually planning on doing a review session tomorrow. I'm working with some of your classmates on setting that up. But I'm thinking tomorrow we'll do a review session to cover all the exam content, at least some practice problems, at around 12:30. So today we're going to go ahead and we're going to go through the Claisen condensation. We're going to go through the aldol reaction, beta dicarbonyl chemistry a little bit with esters, and then we're going to do Michael addition. Keeps freezing. I'm not sure what the deal is, guys. Hang on, let me check if we have a tablet that's online too, and my switch as well. Hang on 1 second. Hey, Tristan! Tristan!
What?
Are you on the
I'm just playing.
Are you on the tablet?
No.
Okay, because I'm lagging really bad. I gotta fix the Wi-Fi.
Okay.
Where's the tablet?
I'm coming.
Where's the tablet?
Right here.
Can I see it?
Yeah.
Yeah, I'm lagging really bad, so I gotta turn it off. Right. So turn up the Wi-Fi and everything, so it should be better now. So sorry about the lag. Anyway, like I was saying, we're going to go through the rest of the Enolate chapter. Let's just go ahead and get started. Offline. I just yelled loud so you can hear me. All right, sorry about the technical difficulties I'm having here. Like I said last time, I upgraded my internet and I also turned off everything, so I don't know why we're still lagging if we are. So I'm going to go ahead and start. So the first thing that I want to take a look at here are Claisen condensations. So Claisen, fucking shit. So I'm lagging again. All right, so we're looking at Claisen condensations. The way you want to remember these are, remember that I said last time that we're going to be working with enolates now, and we're going to basically revisit a lot of old reactions. So essentially what a Claisen condensation is a enolate nucleophile doing an acyl substitution. So once again here, a Claisen condensation is essentially an enolate with an acyl substitution. So let's just go ahead and take a look at an example. All right, so here we have ethyl acetate. And it turns out that we also have acidic H's here. Remember, the anion of this would be resonance stabilized. So here, so I want to point out here, so here we have an ester that we're working with. Let me go ahead and write that in green. Oops. When you're writing out the reaction for this, when you choose your base, you want to choose it to be the alkoxide of whatever this alcohol piece is on your ester. So the reason why we do that is because if you have an acyl substitution happen with this, you get the same product back. So if this were to sub out this group, they're the same, it wouldn't make a difference. So the only thing that really matters here is the acid-base reaction that could happen. So you want to show a deprotonation of your alpha hydrogen. Like that. Remember the step here looks just like an E2, the same kind of arrow pusher that an E2 had. And yes, guys, I am aware that I'm lagging. It'll be fine when the video actually publishes. It's usually just fine after that. Well, I'm going to have to keep continuing, guys. I can't keep stopping for the lag. I got to keep going. If the lag is too bad, you're just going to have to catch it after it posts. Anyway, continuing here, we now have an Ester Enolate. And this is going to be a nucleophile in our reaction here. What's going to happen here for our electrophile, as we saw back during the acid chapter, that esters can undergo an acyl substitution. So it's essentially happening with itself. So we can show another mole equivalent of the ethyl acetate. I don't know why I'm lagging so bad. I'm getting it on my end too. It's showing me that I'm lagging. Hang on, let me close up other stuff on here. Only thing else I have open here is Steam. That shouldn't make a difference. Alright, so same kind of arrow push we saw last time. You reform the double bond. This goes out and attacks. Let me get that. On this part here, you definitely want to be really careful on your carbon counting. So the part I drew here first is this part of the molecule that I just drew. And then we have our alpha carbon. I'm going to make sure I label the alpha carbon here. And essentially what we're going to have now is we're going to have this alpha carbon is going to be bonded to this carbon here. So I'm going to go ahead and highlight that as a red, our new bond. That is our new bond. And then we have our O minus, we have a methyl, and we have our OET. Like so. Oops. At this point, you can go ahead and show the carbonyl reform and kick out the leaving group. So reform, kick this out, like so. All right, definitely be careful on your carbon counting here, guys. So we had these two carbons are now bonded to these two carbons. So we should have 4 in that straight chain there. So 2 plus 2 is 4. Another thing that's typically shown also with this is that we typically have excess base around. And as we're going to see here in a moment, there is a quench step that is required for this. So it turns out that this can undergo an acid-base reaction forming another enolate. Like that. Really looks like Jar Jar this time. So if that was our step 1, our step 2 is going to be an HCl quench. This is our quench step, and then we are done. All right, so the one little comment I want to mention for this before we move on is that so notice how I am deprotonating from this carbon twice. A lot of time when people run these reactions, this particular ester typically has 2 alpha hydrogens available. So I want to mention that the starting ester usually has 2 alpha hydrogens, like so. All right. I'm assuming you guys can see me now and hear me. Does anybody have any questions about the Claisen condensation? Once again, just to make sure you guys are understanding what's going on here, we have an enolate doing an acyl substitution. So if you actually ignore that the complexity of the enolate and just think generic nucleophile, it's kind of the same thing happening here. All right, I'm going to go ahead and continue, guys. If you're able to hear me, remember you are able to ask questions as we go along. All right, the next example I want to take a look at is the Dyckman condensation, or Dyckman. I think it's pronounced Dyckman. So Dyckman condensation. This is basically a intramolecular Claisen. So the question was, why do we use HCl as a quench? And it turns out that you typically have excess of your base, and this basically forms another enolate. So this is reactive. Typically, if you have something still reactive in solution, you have to quench it. So the HCl basically just protonates. Let me draw the arrow in, just make sure that we have the arrow here. Yep. So then we get our neutral product there that's unreactive. All right, so this particular compound is a diester. Make sure I get my carbon counts right. 1, 2, 3, 4, 5. 2, 3, 4, 5. Okay, so this is going to be the compound that reacts, and the way you want to think about, I mean, we could draw out the mechanism for this, but I want to show you guys how to predict products here. You don't want to have to always predict or draw out the mechanism every single time, but essentially what's going to happen is the alpha carbon is going to trade out the bond to the OET over here. So essentially what's going to happen is this is going to connect here like that, and we're going to lose that group as a leaving group. So I think the best way to predict products here is to actually just number your carbons. So I'm going to go ahead and number them as, I'll just go ahead and start with the alpha carbon being number 1. So 1, 2, 3, 4, 5, and 6. So what you can do is just draw a ring that is that size, and then you just tack on the pieces, remembering to remove this leaving group. So let me go ahead and fill in the conditions. The condition will be the same as the last one, NaOET, and then 2 would be a HCl quench, and then we get a 6-membered ring, like that. And then I'm going to go ahead and number my carbons in here. So I'm using red. So 1, 2, 3, 4, 5, and 6. The new bond is between carbons 1 and 6, so you can highlight that if you want to help make more sense of it all. So there's our new bond. And then over here we have, that's this carbonyl that I just drew. And then on carbon 1 we have the ester group coming off. Like so. So an intramolecular Claisen has its own name for it. Okay. So we're going to see in this coming section that these beta dicarbonyls are actually really useful for other types of synthesis. So this is an example of a beta dicarbonyl. Like so. All right, I see someone is typing. Maybe it's a question. Oops. That's all the potential. So the question was, will the HCl hydrolyze the ester? Possibly if you apply heat. Typically if you are doing a esterification cleavage, an ester cleavage typically requires heat. So that definitely, this is all equilibria, so that would definitely be a side product, is the hydrolyzed ester. So when you guys are getting your 50% yields, so what part of this indicates the alpha versus beta? All right, so the question was, what part of this distinguishes between alpha and beta? So typically we're talking about from the carboxylic acid derivative. So this is the main carbonyl we're looking at, and then it goes alpha, then beta. Where'd my green go? There. Alpha, beta, like so. Yeah, it's typically from a carboxylic acid derivative if you have more than one of them. All right, so let's go ahead and take a look at some the enolates of beta dicarbonyls in a little bit more detail. All right, so we have this one, and then we're going to take a look at specifically the acidity of these H's in the alpha carbon. Hi, Tristan. Are you running in the house again? Yeah? I think it's okay. Okay, so out of these two here, which one do you guys expect to be more acidic for these alpha hydrogens? So this one or this one would be more acidic. So left or right? And I'm going to have some pKa's to compare them with. So typically when you're thinking about acid-base chemistry, you kind of want to think about what the anion is going to look like, especially if there's going to be resonance involved. Yep, you guys are, everybody's saying the second one, this is correct. It works out where the pKa for this one, I mentioned last time, with about 19. The pKa of this one is about 10. And there is a 9-degree order of magnitude difference. Remember, your pKa's are logarithmic scales. So these are 9 orders of magnitude difference. And if you guys would guess that resonance is the explanation, remember, if you're guessing resonance, you're right a lot of the time in organic, and that is true here. So what you can show is the resonance of the anion. There, starting with jar jar. So I'm basically going from there to here, minus H plus. And then you can show resonance for this. So the more resonance you have, the more stable the anion is, the more acidic that H is. So we could draw resonance where the enolate goes here. You also could draw resonance where the enolate goes on the other side. Like that. All right, and then let me just go ahead and fill in the arrow pushes here just so you guys are understanding how the arrows work. So it goes like that to go to this one, and then to bring it to this one, we have to go that, that, that. All right. So it turns out that the next section here is we're going to have a useful beta dicarbonyls for synthesis. The two main ones we're going to take a look at today are the aceto acetic ester. It's this one. I believe that was the product for something that we did earlier. I think that was the first reaction we did. This is called aceto acetic ester. And the other one, or sorry, the other name for it, if you guys remember your nomenclature, would be ethyl 3-oxobutanoate. So this would be the official IUPAC, but that's more of a common name for the aceto acetic ester. The other one we're going to look at is where both sides are OET. That's the main difference here. And this has the IUPAC name of diethyl malonate, and we're just going to call it a malonic ester. So malonic ester are the two different names here for these guys. Yeah, so these are very useful for making different kind of compounds. You're going to see here. All right. So the first reaction I'm going to go through is acylation. I think the key word in there should be acyl. Hopefully you guys know now what that means. So here we're going to go ahead and start with our aceto acetic ester. Like that. And then we're going to use the same kind of base as we used in the last one. And we're going to start off by making an enolate. So first step here is to deprotonate, like that. And then what I'm going to throw here is an acid halide. And I'm going to make a little comment here that you want. You basically want a acid derivative with a good leaving group. And if you guys remember what these were your acid halides and anhydrides. It's typically what you want to do this with. And then the next step that's going to happen here is going to be an acyl substitution. And let me add some other notes here. This was acedo, acetic, ester. Like that. So the arrow pushes are, as you guys probably expect, is we get a nucleophilic attack on the carbon. Like that. And then I'm gonna keep saying it all through this chapter. You need to make sure that you count your carbons. Counting carbons is crucial in this chapter. And I like to always highlight new bonds too. I did this as a student as well. Back when I was in OChem, I always used the red or orange to highlight the new bond. But the new bond is right there, the alpha carbon. And then we have what? We have an O negative. We have a methyl. We have a chlorine, like that. All right, and then that was the tetrahedral intermediate that you have for the acyl substitution. So count your carbons, guys. Be careful of your carbon counting. So essentially what we have now is, instead of having this with a chlorine attached, it now has this whole thing attached. And that's this carbon down here. So if you wanted to, you could mark the carbons here. I'm going to mark this one with an asterisk. So that carbon is this carbon is this carbon. So we can use that to help keep track. So whatever you got to do to do your bookkeeping, to keep track of everything, that's what you want to do. Typically, so the next part is the workup. So I'm going to add that part here, the workup. I want you guys to help me with what happened. So the first step of the workup is sodium hydroxide and heat for this part. And then what ends up happening here is like that. So what we did here is we went from having an ester to having an acid group. What was the name of that reaction? So once again, the question is, going from an ester to a carboxylic acid, what is that reaction called? This is fair game for the exam. Anybody? Yep, so this is saponification. This workup. Yep, people are asking saponification. That is correct. So the next part here is just, typically we have H3O plus in heat. And then we have our final product is like that. So what do you guys think happened here? Going from here to here, what do you guys think happened? And this is a beta diketone product. So once again, the question was going from here to the final product. Yep, that is a decarboxylation. Correct. So decarboxylation. Nope, that was a decarboxylation. We lost this group. Notice here how, remember for decarboxylations, we had to have a beta keto acid. We have two ketones in the beta position, or sorry, we have a ketone right here in the beta position, as well as down here. So let's just go ahead and label those so we're all clear. Alpha, beta. There's two beta ketones there. So this is a beta keto acid. Like that. All right, so the main thing that you want to think about with these is if you actually take a look at the starting compound, you're essentially replacing whatever the ester is with whatever the acyl group is on the acid group. So basically, instead of having attached to Cl, it's basically whatever is on alpha is this is where it's attached now. So if we highlight the new part, I like highlighting the new part. So this is the new part. There. That whole part was new, and then this was the alpha carbon from the original alpha carbon. So the net takeaway is the acyl group substitution at the alpha carbon. All right. The next reaction here is another similar setup here where we're going to be doing some kind of enolate chemistry, some kind of substitution, and then we're going to end up doing a similar thing at the end. But our starting point is the main difference. So the next one I want to take a look at is the malonic ester. Synthesis. Like that. So we're starting with the malonic ester, which was the ester that had the two ethyl groups on both sides. Like that. And then the first step here is we're going to go ahead and, oops, the same base, sodium ethoxide, ETONA. The second step here is going to be an alkyl halide. So I'm just going to put RI there and leave the comment here that this is an alkyl halide. The first step here is a base to form the enolate. So what do you guys think is going to happen here? So the first step is making an enolate, and then the second part here we have an alkyl halide. Essentially what happens is whatever the R group is will be attached to the alpha carbon. And we get R attached there. Like that. This was an SN2 that's happening there. All right. The next part we're going to do is we are actually going to be effectively cutting off two parts of the molecule. We could run through all the details here, but you do have all the details for each step in your notes elsewhere. We're just kind of wrapping things together now. But the next step, what it's going to do, it's going to basically clip right here and right here. We're basically going to lose both of the alpha groups. So what's going to happen here is we are going to have a carboxylic acid, and then R is attached to the alpha carbon. Like that. And the reagents for this, the first step is NaOH and heat. The second step is a quench with acid and heat. All right, and then we now have a carboxylic acid. All right, so I like to label alpha carbons too to help keep track. So alpha carbon, those are all the same carbon throughout the whole process. The first part was a saponification. And the second part is decarboxylation. Yes, it's very cool. So I think this would be a great practice problem to run through all the mechanism for. We have covered all of these pieces throughout the previous notes. So this is one I recommend doing. I want to go ahead and show you an example problem we could do with this. And I could do some mechanism detail here as well. Tristan, you need to be quiet, please. You're making too much noise. All right, so I want to just go ahead and run through arrow pushes here just to make sure you guys are understanding everything. And I think we kind of have the time for it anyway. So first step, deprotonate. We get our enolate. That one's almost dead on lead. All right, and then what we can do here now is take that, and we can do an SN2. And then we have this. The first part, I'm actually not going to do the mechanism here for this part. This is a saponification. We're essentially going to turn both of these groups into carboxylic acids. Like so. We now have that. And for this next part here, I'm actually going to redraw this part. I actually want to show this arrow push. So let me, I'm going to change the orientation just for making the arrow push a little bit easier to see. So I'm making the OH go this way now, and then double bond O goes that way. So what's going to happen now is we're going to get that. Like so. The reagent for this is H+ in heat. This is the decarboxylation. So this part you want to be careful on what you draw. So we have our OH. We have an OH like that. And then we have our double bond. We get that. And then this can tautomerize to the final product. Remember, the final product is just going to have whatever R is, which is this piece, attached to the alpha carbon. So alpha carbon, which is that carbon right there, and then we have one, that. So there's the 4 carbon fragment right there that is attached here. So let me highlight the new bond. Like that. All right, let me fill in some details here, and we'll be done with this one. This is saponification. This step here is decarboxylation. And then this part is tautomerization. All right. Hi, he doesn't have a shirt on. Where's your shirt? Are you hot?
I got hot.
You got hot? It's okay. Why don't you go outside in that wind? It'll cool you off right away. All right, do you have any questions about the ester reactions? These ones take practice, guys. These are pretty long. I recommend doing practice problems and practice the mechanisms, because these pretty much go over all the mechanisms for the exam, don't they? Just about. Yeah, all these mechanisms are on the exam, potentially. They're all kind of new. I think the only thing not new here is probably the SN2 part. All right. So if you guys don't have any questions, I'm going to go ahead and continue. Clear as mud? All right. So we actually only have one more reaction to go, right? Just one more reaction. But it's going to take like 20 minutes to do it. So the next section here I want to talk about are the alpha beta unsaturated ketones. Oops, I'm using this one. Alpha beta unsaturated ketones. So it turns out that when we went over the addition of aldehydes and ketones earlier, we didn't show you the whole picture. We're going to get the rest of the picture today. So it turns out that these are electrophilic, so these are electrophiles, but which carbon is the electrophile is the difference here. So let me go ahead and draw this out, what we're talking about. So here we have alpha and beta. So when we say alpha beta unsaturated, we're referring to here we have unsaturation at the alpha carbon. And there's two ways that the nucleophile can attack. So I'm going to go ahead and draw it out twice and show you the different versions. What? What'd you say?
I said Daddy's talking about backside attacks.
No, I'm not actually. All right, so the main distinction here is we're going to have a strong nucleophile versus a weak nucleophile. So notice how I'm trying to show it a little bit different. But here we have this one is strong, this one is weak. So what we saw previously this semester was that with the strong nucleophile, these can actually attack here, like so. And we get O minus, and then whatever nucleophile is attached like that. If you have a weak nucleophile, it turns out that this carbon over here is actually electrophilic. So the beta carbon is electrophilic. And I'll show you why with resonance in a second here. So what happens is we get that. So now what's going to happen here is instead of it being attached directly to the carbonyl, the nucleophile is going to be attached at the beta carbon. Like that. And then what we can do here, oops, I think I skipped the aldol, didn't I? I totally skipped the aldol reaction. We'll go back to the aldol after I do this part. Anyway, we'll then have an H plus step. Oop. I wrote who there. I was thinking H. All right. So nucleophile. And then now we have an enol, and then this could tautomerize to your final product. Like that. All right, so we have two different ways to talk about these. The first way that, this is back from, a few chapters ago, this is what we call a simple addition. Simple addition. And the lower route has two different names for it. One is conjugate addition. Conjugate addition. The other name you may see for this is Michael addition. We named it Michael. Yeah, so these are or. All right, so quickly here, the reason why this can happen is because if you actually draw out the resonance for this, you should end up with a plus charge over here. So drawing some resonance here, you can move this up like that. And then you can draw another resonance structure where this moves over like that. So then double bond is now there, O minus, and then plus is over here. So if you look at the resonance hybrid, you end up with a delta positive on 2 carbons. So this is the resonance hybrid. It's like that. And then you end up with a delta plus, delta minus, delta plus. So it turns out that these 2 carbons are electrophilic. If the nucleophile goes there, you call it a conjugate addition. And then if the nucleophile goes there, we call it a simple addition. Like so. All right. Are there any questions about this so far? The 2 types of additions that can happen, whether simple or conjugate. Any questions? Then the first question that may be coming up in your head is which nucleophiles do what? And everything we used previously pretty much go the simple route, so all the other nucleophiles that we didn't talk about during that chapter come up here. So I'm going to make a little list for you guys. So your nucleophile in this list is going to be for simple addition. Let me fix the lead in this pencil. Simple addition. These ones are your hydroxides, like your OH minus, your amides, ions, these NH2 minuses, and then Grignards. These are all strong nucleophiles. And then your other route over here, your nucleophiles for conjugate addition. Are pretty much all the other ones. So I do have a list here for you though. Your thiols are weaker. And then you have your cyano groups. Those are also weaker nucleophiles. Amines. These amines are not charged. They're neutral. Enolates. I do want to mention here though that if you're specifically using an enolate, this is what the Michael addition is. Yeah, so once again, if you're doing a conjugate addition specifically with an enolate, we call that a Michael addition. I'm going to show you an example of that here after I do this list. The last one that go in this category are Gilman reagents. These were your organocuprates. You guys may remember working with these reagents earlier this semester. They were kind of alternatives to Grignards, but it turns out that they are a weaker nucleophile than a Grignard is. So these are weaker nucleophiles, like so. All right, so the example I have here for you guys go ahead and do that. And then the reagent I have here is sodium cyanide. And as we see up here, this is part of the conjugate addition nucleophiles. So we're going to show a attack here, like so. So instead of having no attachments at the alpha carbon, this time it's at the beta carbon. So new bond is here. That's the new bond. And we now have this. You can show it picking up an H plus from somewhere. This is probably happening in water. You can probably pick up the H plus from water. And then we still have our enolate though. Hi Tristan. What are you doing? What are you doing? You try to hide from the camera? I think they see you.
I'm trying to be in it, but not trying to show my body. That's what I'm trying to do right now.
You could always go put a shirt on.
All right.
Yeah, but I'm still hot.
So we now have that. Are there any questions about this so far? Any questions? I usually have a lot of questions about this when we do it in class, so I wonder if you guys are able to see me. Am I even streaming? I'm starting to wonder, am I even streaming? I think I am. Yeah, I'm streaming. Dude, please stop. Just go somewhere, please. Just go somewhere. Okay. All right, let me go ahead and do another example here. So this would be the kind of type of problem you would see on a test. Basically, predict the products here. Okay. So thinking about what's going to happen here. So what's going to happen here is this is going to form an enolate. I would do it with this one. This is going to be this alpha carbon. And we have our alpha and beta carbons here. So what's going to happen now is on this one, so this is going to be our nucleophile. This is going to be our electrophile. We're going to have a new bond between the alpha carbon on the nucleophile and the beta carbon on the electrophile. So I'm just going to go ahead and draw the result of that. So this is the nucleophile. We're going to have a new bond right here. And then we have the rest of this piece attached. So 1, 2, 3, 4, like that. So this is the new bond we highlighted, and if you have an enolate as your nucleophile, we specifically call this the Michael addition. Michael addition, like so. All right, I did want to do the mechanism for this just to make sure that you guys are all understanding what's going on. So the first step here is a deprotonation. We're going to deprotonate here. Like that. So I'm showing a different way for deprotonation here than I did the last time. You can show this a couple different ways. You can then show resonance of the enolate. Like that. And now we got the fun arrow push now. All right, and then I'm going to label alpha and beta. Alpha, beta. So we're going to basically reform the carbonyl. This is going to go out and grab the electrophile, which is going to be the beta carbon on this one. This has to move over. This has to move over. So I know I'm not the biggest fan of 4 arrow pushes, but we have to here, so we don't have a choice. And I'm going to add the little comment on here. Enolates do conjugate addition. All right, so then draw the result of that. We have our double bond back on the carbonyl. We have our new bond there. We have a double bond here. O minus, like that. And then there's two ways you can show this quench. So like in the last mechanism, what I showed you guys with the H plus was I grabbed the H here and then I did a tautomerism. You can actually show the tautomerism now. I've seen it done this way as well. So I'm going to go ahead and show it that way. So if you actually compare this mechanism to the last one, I do this step a little bit differently each time, and they're both equivalent to each other. Like that. And again, if you wanted to, you could draw your product a little bit differently. This is a 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, and then double bond O, and then that. So honestly, if this were a multiple choice question, this is kind of how the product would be drawn. So you have to be able to twist them around like that when you're answering your questions. Yep, that's right. Yeah, the question was, the last part is just tautomerization. That is correct. I was showing it two different ways here. All right. So before I do the last one, I did need to find my notes on the aldol. Enolate is where you have a double bond with an O minus on it, like that. Double bond with O minus is enolate. Where are my aldol notes? There we go. All right. So let's go ahead and take a look at the aldol reaction, and then I have one more reaction after that where we kind of bring all the stuff in the chapter into one problem. And that will be where we end the class today. So the next part here is the aldol reaction. This reaction is basically an enolate addition to aldehydes and ketones. All right. So as you guys can probably guess, the first step in this reaction is to form a enolate. But before that, I want to show you guys how we predict products here, and then we'll do a mechanism. So essentially what's going to happen on this, so it's this, we're going to suppose this is going to be a self-aldol. It's going to react with itself. So what is going to happen here is we're going to have a carbonyl, the aldehyde or ketone. Instead of having a double bond to O, it's going to have double bond to alpha carbon. So it's going to have a double bond to this alpha carbon here. So the conditions here are hydroxide. So we have the first part. So this part would act as the nucleophile, and then the other mole equivalent of the acetone would react with itself. And like I was just saying here, instead of having double bond to O, it's going to have double bond to alpha carbon, like that. And I'm gonna add that note here. Double bond to O replaced with double bond to alpha carbon instead. All right, so for my examples here, I have I'm going to show you the self-aldol with acetone, and then for the, I have a mixed aldol, which I'm going to do the reaction from lab. So if you guys did the lab already, I'm basically going to do that here with my example. All right, so mechanism time. Remember, you guys did see a couple times ago that we can show this doing a simple addition, but in order for it to do an aldol, though, it has to do a deprotonation. So I'm going to go ahead and show the formation of the enolate. like that. O minus. And then if you're doing a self aldol, it'll react with another mole equivalent of itself, like that. And then this is going to be your nucleophile. Your enolates are always your nucleophile, and then something else is your electrophile. So in this case, itself is the electrophile. So do our typical arrow pushing for an enolate attacking, like that. But here we have an extra arrow push doing that. So we have our double bond O. This is our new bond right here. And then here we have an O minus, like so. Because this, we're using hydroxide as our base, we can show water here acting as an acid. So I'm going to go ahead and protonate. So here we have our OH, like that. So sometimes the reaction stops here, but usually it doesn't. So I'm going to add that little comment in here. Sometimes reaction stops here. And this is a beta hydroxy ketone. It turns out these easily eliminate. Easily eliminate. So what we can show now is we can show another hydroxide doing an an E2. This next step here is an E2. So we're going to grab one of the adjacent H's. Like that. New double bond knocks out the leaving group. That is exactly an E2. Double bond is now here. We have that. We are done. And our product, hey, if you think about it, we can now do something with a Michael addition now, right? This is a Michael addition compound. This is an alpha beta unsaturated ketone. The reason why these compounds eliminate so easily is because this has a conjugated pi system now. It's more stable. So this is more stable due to pi bond conjugation. Oh my goodness, all these concepts are coming together from the whole year are coming together in one chapter. All right, so there's your self-aldol. The next reaction I want to go ahead and show is the one from lab, the mixed aldol that we were supposed to do this week. Remember, you guys have asked any questions, I'm going to go ahead and continue. You guys can ask questions. So the next one I'm going to do is mixed aldol. Will the OH have to be protonated first? So the question was, would the OH have to be protonated first on this here? I wouldn't do that because we are in base. So that would give you a plus charge in your mechanism. So we are in hydroxide. It's actually okay to show hydroxide as a leaving group if you're in hydroxide. So I would not protonate first here. Yeah, so the reason why OH is being a good leaving group here is because we're already in hydroxide. We saw that earlier with the... hang on, we showed this earlier also, where we had like a bad leaving group, but you were already in that kind of solution. Here, I think it was? No. Yeah, so the first reaction I did today, I showed this, and then we had a bad leaving group leaving. So the reason why that was okay here is because you're already in this kind of medium. Yeah, so it's normal to show that. If you're already in that kind of solution, you can show it at the leaving group. And this is the further thing driving this here is that this is actually more stable than this is. So the reaction usually does not stop here. It usually goes to that. All right. So getting back on track here, we're taking a look at the mixed aldol. Usually when people do these reactions, they will use very specific compounds. The one we're using for today's example is going to be benzaldehyde and acetone. All right, so we have that. And then I'm going to space these out. I'm going to put notes under everything here. We have that. So here we have an aldehyde with no alpha H's. So not only do we have an aldehyde, which is strongly electrophilic, you have no alpha hydrogens, so the base cannot make this a nucleophile. So this cannot become a nucleophile. This is going to be your nucleophile. So this part, your ketone, forms an enolate nucleophile. So what's going to happen now is because this is our electrophile here, this is our E+, instead of it having double bond to O, it's going to have double bond to alpha carbon. So it's going to have double bond to here. So what happens here is double bond, then benzene. So this piece right here is this piece. And then it turns out for this particular lab, it happens again to both sides. So we're going to get the reaction happening on both sides. Like that. And this compound was the dibenzyl acetone. It works out when, if we ran this in lab, what you would have seen is that this compound is orange and this compound is yellow. So it turns out you do get quite a bit of this forming, but most of it is this one. And the point of the workup for the recrystallization was to get rid of any of the orange color, so you get a bright yellow precipitate at the end. It's almost like a chalky yellow color at the end, where it's more like a yellow-orange before you do that part. And this label here, so alpha, alpha, alpha. Yeah, so I recommend tagging things and then counting carbons. Make sure you don't lose track of carbon. That's the most common way students lose points is they lose track of carbons, and then they give me a whack product. So yeah, be careful of your carbon counting. All right, so I literally have one more problem to work through, and then we're going to be done. Aren't you guys so excited? We're almost done with the Enolate chapter. Now you'll have to just study a lot. Yeah, let's take a look at the Robinson annulation. All right. Robinson annulation. So once again, I'm going to show my nerdiness here. So when I see this reaction, I imagine this is what the Robinson family was working on while they were lost in space. If you ever seen Lost in Space, they're the Robinson family. And I actually used that to remember this when I was in college. But the word annulation, this is a fancy word for ring formation. Danger, Will Robinson, danger! Excuse me. All right, so for my example here, we're going to start with a cyclic ketone, like that. And then we're going to say this is reacting with a alpha beta unsaturated ketone, like this. So based off what we talked about so far, what do you guys think is going to be our nucleophile in this reaction? The conditions are NaOET. So based off of what we've learned so far today, which is the nucleophile? This one or this one, left or right? What is the nucleophile? The nucleophile is actually going to be the left one. These are going to be electrophiles. So your alpha, beta, unsaturated ketones are typically electrophilic. This is going to be the nucleophile. So I'm going to write this out. So nucleophile, electrophile. Let me show you the final product, and then we'll work to the mechanism. So the final product is probably not what you would expect. We're going to get a bicyclo compound from this. We already have one ring on there. We're getting a new ring. To help you keep track of your carbons, I'm going to label carbons here. So I'm going to basically mark these with big red circles. So we have those 4 carbons are these 4. Wait. Let me just double check. Yep. Is that right? I might have made a mistake. Hang on, let me double check. No, that's right. That's right. Yep, so these 4 carbons are these 4. Just double check my notes, I'm right. So let's go ahead and take a look. We're going to be applying a bunch of different stuff we talked about today in one problem. And I will, as per usual, write notes as we go along. So the first thing you want to do is show the base acting, or the base forming an enolate. So go ahead and show that. So attack the alpha hydrogen in an E2-like fashion. Remember, that's an E2-like step. I'm putting quotes there because it's technically not an E2. It's just an acid base, but the arrow push looks just like the E2 did. All right, so the next part here, we have an enolate nucleophile at this point. And then you can go ahead and show it reacting with the electrophile in a Michael addition. So this next part here is going to be a Michael addition. And the way we showed that was enolate attacks the beta carbon, like that. We get that. I always like highlighting new bonds so we can emphasize where the new bond was at, and it also helps me keep track of my carbon count. So we have our 6 original carbons on there. We should have 4 more over here. So there's the new bond at the alpha carbon. 1, 2, 3, 4. And we also have the enolate at this point. Like that. You could then show it tautomerizing by picking up an H. So just like before, you can go ahead and show this picking up an H separately and then show the tautomerism as a separate step. Or you can show it all at once here. This is like the shorthand that I like to do. This is another shorthand. But I guess you could show that as 2 separate steps. So double bond O, 1, 2, 3, 4, like so. All right, so now is the cool part. So here we can show these hydrogens. All right, so previously in the past, we've shown, so what I'm going to be doing next is forming another enolate. Typically, we formed with the inside one, not the outside one. But I'm doing it with this one here is because this is going to connect to here. And it's an issue of ring size. So if this one were to attach here, that would be a 4-carbon ring. And if this one attaches, it's a 6-carbon ring. 5 and 6 membered rings are more stable. You should have learned that last semester in 241. Yeah, so whenever you get these reactions, they're forming a ring. Typically, if you look at the ring size, they're always 5 or 6. They're never like bigger than that or smaller than that. They're always 5 or 6. So I'm going to show another mole equivalent of NaOET forming an enolate. Like that. All right, I'm going to add the little comment here that I just said. I just want to make sure you guys are understanding what I just said. So at this point here, you want to consider the ring size when you're deprotonating on this step. So this is going to make a 6-membered ring. If we took the other alpha hydrogen, that would be a 4-membered ring. So consider ring size when deprotonating here. We're going to get the more stable ring. So here, we do that. This goes out and attacks there, like that. And we're going to call this part a intramolecular aldol. So intramolecular aldol reaction. So I want to highlight the new bond as well here. So here we have an O-. Our new bond is right there. That is the new bond. And then count carbons here. It's going to be 1, 2, 3, 4, 5, 6 carbons. Like that. That is a 6-carbon ring. And then our double bond O here. So our double bond O should be 3 atoms out. So 1, 2, 3. It's right here. Like that. All right. You can then show it picking up an H from the NaOET again. Or from ethanol, rather. So pick up an H. So we have an OH here, double bond O. And then like we saw at the last example here, we can do a E2 elimination for the last step, and then we're done. So I'm going to use NaOET again for our E2 step. So you want to deprotonate, double bond, leaving group. Like that. And then we are now done with the Robinson annulation. I was talking about, the Lost in Space. There's actually a Lost in Space series on Netflix right now. It's pretty good. There are 2 seasons in so far. I enjoyed both seasons. First one was better, though, than season 2. But if you guys are bored and want to watch TV, there's stuff on Netflix. All right, so we are now done with the Enolate chapter.
And I do not watch Netflix.
You don't watch Netflix? Here, Tristan, come here. I want to see what he thinks of this. So what do you think about what they're learning? Look what they're learning. Look, I just drew all that. What do you think?
It looks confusing.
It looks confusing? Do you guys think it looks confusing also? Alright guys, I'm actually, this is actually good timing. We're actually at the end of the chapter, and we're also, if we were in lecture, we would be about out of time as well. So I'm actually going to end it here, unless you guys have any other questions. It looks like a headache. I agree. So the thing about this chapter I keep trying to point things out to you guys. We literally have just a new nucleophile, and we're just applying it to old reactions for a lot of it. So a lot of it's kind of intermingled now from the whole year. So just try your best to distinguish between the similarities and differences between everything, because it's a lot of repeat here. I'm hoping you're seeing the repeating stuff happening here. And I'm not tarnishing his brain. I'm helping him learn basic STEM education. Nothing wrong with OChem at 6 years old. It turns out that so the question was, why did it form the second ring instead of stopping there? So instead of stopping here, and it turns out that the ring is actually more thermodynamically favored than the straight chain is. Yeah, it's a thermodynamics thing. This one is favored. Let me switch over to the face cam. So the statement was, I was like, there's no problem with OChem at 6, and then apparently there's a problem at 36. You guys can do it, right? OChem survivor, help, I'm dying. That's what it says. Help, I'm dying. Is that how you guys feel right now? Like that? Like this guy on my shirt? Yeah, you guys are really doing a good job of surviving right now, doing this all from your houses. I couldn't imagine when I was in OChem doing it from home. I needed my classmates. Oh, so funny comment here. So a few weeks ago they were doing shapes like cube, sphere, cone. I had Tristan draw on a tetrahedral on there, and the teacher circled it and said, "Daddy must have helped." The teacher knows me, so. All right, guys. So I think we're at a good stopping point for the lecture. As I mentioned, I'm thinking about doing a review session tomorrow at 12:30. So I would like for you guys to tune in if able to. If not, you can catch a stream sometime, on YouTube during spring break. But I'm going to go ahead and cut the stream here. I'll be in Discord for any additional questions as usual. And on that note, stay cool.